Hello everyone, welcome to this KANPUR-NPTEL online course on space environment and its effects on orbital spacecrafts. So, these days we are discussing the spacecraft charging, which is one of the profound effect of the plasma environment on the spacecraft. And in this regard, in the last session, we discussed what is the spacecraft equilibrium potential, also we call it the floating potential. And then we discussed how this potential is built up. That is, there is two action, one is the repelling of like charges and the attraction of opposite charges. And as we explained that whenever a spacecraft is emerged in the plasma environment, so the electrons, because of the lighter mass, these are accumulated before the positive ions can get accumulated or the protons can get accumulated. So, as a result of that, the spacecraft get negatively charged. So, negatively spacecraft will repel the incoming electrons and will attract the positive charges or the positive ions. So, and we explained it how a non-neutral region, that is called the sheath, is created around the spacecraft where the environment is non-neutral. So, we discussed all this thing and then we wrote that is the expression for this incoming fluxes or the what are the species which are attracted and the species which are repelled in terms of the that is the Maxwell and the Boltzmann, that is the velocity or the energy distribution function. And then we defined a factor, it is called the Boltzmann's repulsion factor. It is because whenever suppose the ions are attracted. So, the ions attain or the energy. So, whatever the energy is there in the neutral plasma, whatever the distribution is there, the energy distribution, that gets shifted. So, that is given by the Boltzmann's repulsion factor. So, we discussed all those topics. And today we will continue with all those topics. So, what we are going to discuss today, that is the current valence equation. So, before we go to the current valence equation, we need to know what are the different the components. We only considered the two components, that is the primary, that is the primary either it is electrons or the ions, but there are the other components. So, we will see what are those different current components. So, this is the thing which I just discussed yesterday. So, just I like to have a recapitulation. So, what I told that is this part it represents the distribution, but here we have taken the logarithm of the distribution function. So, now it has become an equation of a straight line which is given by this. So, if you consider this one, so this represents the energy distribution when there is no charging, but when the spacecraft gets negative charges and when it is the ions are attracted to it. So, those ions positive ions, because of that this energy that is the q phi. So, as if those they have gained an energy of q phi or they need to do a work q phi. So, because of that what happens, the distribution function they get shifted by this. So, this already we explained. So, then I told yesterday that suppose it is not a Maxwellian distribution, and we will see that the Maxwellian distribution is only valid when the thermal equilibrium is there, and when this the energy distribution or the velocity distribution is defined within a the limit. Beyond some limit, the energy it reduces to 0. So, what I mean to say that the distribution is something like that. So, after that so if you see the distribution, it is going like this and then it goes to 0. So, it means that this is the energy or the velocity distribution what it can have, this particle can have. But suppose the thermal equilibrium is not there, there is the suprathermal particles are there, then this distribution function we will not be able to use it. So, there the other types of distribution function we will see all those things. It is one of the example is called the Kappa distribution, where I can have the energy in the for the tail, in the tail also I can approximate the energy. So, this thing will be there. But here I want to tell you that if even if it is not a Maxwellian distribution, it can be an arbitrary distribution, then also because of that the Ripple that is that species as sorry that yeah they get an energy, additional energy, that is the q phi, and because of that thing this gets shifted. And we have seen that for those species which are repel. So, there the distribution it shifted towards the left side, but since the energy cannot be 0. So, it means that that energy is the lost, means those particles instead of gaining the energy, they lose the energy in that process. So, now the today's topic, that is the different plasma fluxes which are used. So, we just consider the primary the incoming either it can be electron or it is the repel species as the electron, and the species which are attracted by the spacecraft because of his negative potential. So, there are other types of fluxes. Those we will be telling you one by one. So, you see in this picture what we are showing, that those some species are repelled. So, you see all those negatives, the negative particles like the electrons that are getting they are getting the repel, whereas the ions, that is the positive charges, they are getting attracted to it, and it shows that something is coming out from the spacecraft. That also I am going to explain what are those things. That is called these are the ambient, these are all the ambient plasma of the spacecraft. Spacecraft itself can create the plasma particle, that is called the the induced. One is the ambient plasma, and it can be even the induced, means it is created by the spacecraft itself. Okay. Apart from this thing, there are the other types of current which are going to discuss, and all this whatever is happening, that depends on how this material or the surface responds to this ambient plasma particles. It can be in the photoillumination, then triboelectrification. Triboelectrification means whenever the spacecraft is moving at a very high velocity. So, even this neutral particles, because of their the collision with the spacecraft, it can get electrified, or it can become a neutral particle can be ionized. So, that is called the triboelectrifications. Okay. So, again it depends on the material properties. We will see all these things when we do a detailed the analysis of each type of current. So, as already the primary electron fluxes, which we are calling it the repel species, means they are getting it is repelled by the negative potential of the spacecraft. Then the primary ion fluxes, which are this species which are attracted by the spacecraft negative potential. Then secondary electron fluxes. So, I will explain what is the secondary one. Then the other component is called the backscattered electron fluxes. Then we will have proton induced electron fluxes. Proton means when the high energy that is the protons, when they strike the spacecraft surfaces, they can go inside, or even they can create some electron fluxes, that is called the proton induced. Again this is a the secondary electron fluxes. There can be photoelectrons, means the photons, whatever the sun is emitting the photons. So, that can also those can have sufficient energy to excite the electrons from the surface of the spacecraft. Then spacecraft can generate its own plasma fluxes, that also we will discuss. This picture shows this one, this is its own, this is the induced one, the induced plasma. Induced means it is created by the spacecraft itself. Okay. So, all those whatever I discussed, it is shown here. What is the incident electrons, then you are having a secondary electrons, then incident ions, then you are having a secondary electrons. A incident ion can generate a secondary electrons, then there is the photo emission, then there is a backscattered. Some particles it can get even the reflected, it will not have sufficient energy to come and then it will go reflected. So, these are the different components we will explain one by one. So, all those components, all those the types of the currents, they interact with the electric field. Means electric field means inside this sheet there is the electric field, there is a non-neutral region, and they gives rise to they modify the potential. That what is the spacecraft floating potential that is being modified by all these current components. So, now let us see one by one. Primary flux electron flux already we discussed a lot. So, just for the the sake of completeness, I am just writing it here. So, this again these are from the ambient plasma environment of the spacecraft. So, this they play a significant role that we will see, that is the spacecraft potential, the built up potential. It is mainly dependent on all those the primary the electrons or the primary the ion fluxes. And this electrons again it will depending on what is the space weather, what is the condition, what is the solar wind, or this what is the perturbation in our ionosphere. Its energy typically it can vary from few electron volts to few kilo electron volts, depending on the specific space environment, as I already said. And is already because of the lower masses, they are the first this the species which will come first and make this spacecraft as a negatively charged spectrum, and then the process of the start till we get a equilibrium condition, where the spacecraft will acquire a floating potential or a built up potential. Okay. So, this also this accumulation of electrons, this causes the spacecraft to become negatively charged. Okay. So, this also that it repels the ambient electrons to further accumulation. And the primary ion fluxes. So, since the plasma is consists of both the ions and the electrons, so this fluxes they consist of ions, that also impacts the spacecraft surface, because once the spacecraft is negatively charged, then it will attract it. So, these are the incoming the fluxes. Okay. So, this already I said it attracts the positive ions from the surrounding or the ambient plasma environment. Okay. So, this is very trivial statement, that is the attraction happens, the opposite charges attract, leading to an accumulation of positive ions on the spacecraft surface. So, there the recombination can happen, and then eventually we have an equilibrium, that is the incoming the ion flux and the outgoing electron flux, when they will the rate will be the same, and then it will take some time. So, that the spacecraft will get steady potential, or it is the built up potential, and at that time the current, total current or the net current on the spacecraft will be 0. That also will come one by one when we consider the Kirchhoff's current law, that is ingoing current is equal to the outgoing current. So, that will be coming one by one. Now, let us discuss what is the secondary electrons, and this is also very important in the spacecraft studying. We need to consider the the contribution of the secondary electrons. So, what happens when an electron impacts on an atom? It is in general I am telling you, it may impart some of the energy, its energy or thermal or the kinetic energy to the atom, which can result in the excitation or the ionization, depending on the energy available. Means what it can that it can elevate this energy level of the outermost the electron, so that it is in excited state and it will leave the atom. So, what is happening? One electron is coming and it is striking an atom, and atom it is making the atom as ionized. Ionized means it is the electron from the outer orbit, or maybe the inner orbit also it is coming out, and it is giving you a that is a free electron, which is not bounded by the atom, the nucleus of the atom. So, in our spacecraft the similar thing happens. So, when an electron it impacts on a solid, that is the solid surface of the spacecraft. So, the electron may enter to some depth and thereby imparting its energy to the the particles, and it becomes the charged particles. So, as a result secondary electrons may be generated. So, we will see what is that condition. What does it mean? One electron is coming primary, and that can give rise to the number of the electron which may leave also the surface of the spacecraft. So, for each incoming electron impacting on a solid surface, the number of secondary electrons coming out from the solid surface that is given by this probability delta E is this one. So, this is this phenomena, what will be the number of the secondary electrons, that is again a random process. So, it is given by this probability function. So, which depends this function, it depends on the energy E and the properties of this electron. What is the work function, and again it is a function of that is why it is given, it is a function of this energy as well as it is the what is the properties of this solid material which is used in the spacecraft. So, this probability delta E, it can be greater or less than unity. Now, it is something it is since a distribution, it is a distribution function, yeah, it can be greater than unity. It is not a probability mass function, but it is a probability density function. So, it is possible to have, it can have greater than unity also. So, what happens, we will see what is the impact if it is less than or greater than unity, what does it mean. So, for a robust computations, so even we need what is the angle of the incidence, whatever the primary electron, what is the angle of incidence, but getting those data it may not be possible always. So, for most of the practical cases the angle of incidence is not considered, it is assumed that the electrons is striking perpendicular to the surface. So, the angle of incidence is 90 degree, and it can be measured statistically. So, already I said it has to be statistical, it cannot be a deterministic thing in the laboratory, and you can define it as the ratio of the number of outgoing electrons divided by the number of incoming electrons, and that is called the secondary electron yield, SEY. So, we will see different material will have different the values, and there are some empirical formulas, some models are available by which you can calculate what is the SEY in order to calculate the the flux, that also will be coming one by one. So, we will see this figure. Now, you see this figure shows that is that secondary electron yield SEY, that is this axis shows this, and this is at the primary electron energy. Now, you see there are terms E1, then E2, E max, and correspondingly that it is delta max. Then there is a line which is passing, this is parallel to this abscissa, which is the line where the delta or the SEY is equal to 1. So, now let us try to understand what is the significance of this E1 and E2. So, here you are getting two crossings E1 and E2, E1 E2 and a maximum E max. So, you are getting E1 E2 or this is the maximum. So, this is what is the maximum yield and the corresponding energy is E max. So, typically this E1 is about 35 to 45 electron volt, and E2 can ranges from 700 to 2000 electron volt. It again depends on the material to material, these values will be different. So, if this delta max is below unity, suppose if this comes somewhere here, so in that case there will not be U1 and U2 cannot be there, because U1 and E2 are those points where this curve or this yield curve it crosses this the line where this delta is equal to 1. So, if the delta max is below 1, so that question does not arise. So, in that case you will have maybe something like it was something like that. So, in that case there is there is no E 1 and E 2. So, what does it mean that if the energy range E 1 to E 2, if the the delta is greater than 1, what does it mean? It means that there is a good probability that for every incoming electron it can generate more than one outgoing electron. Okay, so that is very important. That is important. So, it should have this delta E should be greater than 1. In that case, that is the probability that we can have more and more more this delta E, the more will be the suppose as for example, if it is 2, then it means that the one electron is capable of giving you more than 1, that is the 2. Of course, this term is always that is why it is called this probability. So, in this range means E 1 to E 2, E 1 to E 2 it is more than 1. So, if I consider this range, if I consider this range, then the outgoing electron flux exceeds the incoming electron flux, implying that positive charging is possible. Means whenever the electron is leaving, so means it is the positive, it will decrease the the level of the negative potential, but generally it does not matter much, because the positive charge voltage whatever is generated because of the secondary electron emission, it is very low, because it has these electrons have only a few electron volt in energy typically. And if the charging voltage exceeds a few positive suppose even, then the secondary electrons also will not be able to leave, because when if it is making it suppose the positive, then they will be because of this the attraction, it will not be, secondary electrons will not be able to leave. So, again the recombination and all this thing will happen. So, this few lines it means that. Physically, if the primary electron is not energetic enough, then it is not possible that it can generate the secondary electron. So, you just consider means it is, if it is in this region, in this region, then it is not possible that we can have a secondary electron. So, for some materials this delta max can reach 2 or even greater, meaning that there can be 2 or more secondary electrons coming out for every primary electron coming in, this already I told. If the primary electron is very energetic, it penetrates too deeply into the material, so that the the secondary electrons generated cannot find their way out. That I will show you the if it goes inside, then the possibility that it will come out as a secondary electron emission, the probability will be very less. The secondary electron which we have seen, it is typically a few electron volt in energy only, and it is to be noted that if the material is very thin, then it is possible that the secondary electron may find its way out from the back side of the material. So, this shows a typical those secondary electron yield for gold for that is primary electron energy range. So, is starting from 0 to up to 24 kilo electron volt, it has been shown here, and you see there are different the curves is not 1, but it is shown here total 6. So, 6 means it is the different the empirical formula used will show you those formulas. So, with this all I was telling, when the electron is having enough energy, when it goes inside the material, then those secondary these electrons whichever they will get trapped inside, they will not be able to come out. Not always, in this figure shows that it is possible that this energy is coming, then it will lose some energy. Okay. That lose some energy, and then it will be here itself, it cannot come out. But even if the after the secondary electron is having sufficient energy, it can generate a tertiary electron, that is also possible. This shows that. So, this is secondary electron. So, this secondary electron is energetic enough and it is capable of taking out one more. Now, we will consider that is called the backscattered electrons. So, we will try to understand how it is different from the secondary electrons. Again it is the probability, we are calling it eta e, that the incoming particle may bounce out elastically. It is not striking it is just bouncing back as a backscatter electron, and here also the probability is eta e, that is called the backscattered electron yield, BEEY. There we got SEY, secondary electron yield, here it is backscattered electron yield. So, the backscatter electrons, they differ from the secondary electrons in two features. What is the first feature? The backscattered electrons has nearly the same energy as the primary electron, because it is bouncing back. So, it is not losing an energy, whereas the secondary electrons feature a distribution of energy, okay, and here this eta e, that is never greater than unity and usually small. So, these are the two difference between what is the SEY and BEY. And delta E is at very low primary the electron energy, few electron volt should be nearly 0, because the energy budget needs to overcome the work function. This we are calling at the SEY. So, this is SEY. However, experimental data it appear to show that non-zero delta E at low energies also, that is also possible. At low energies also you have some delta value, because whenever it is measuring, it is very difficult to distinguish whether it is a secondary electron or it is a backscattered electron. So, as we said that for SE I need high energy electron, but even it is shown that there is some emission at low energy. So, therefore, the the researchers they pointed out that the electrons coming out at low energies are actually backscattered electrons. So, what does it mean that delta E may be that is the secondary electron emission, that is the coefficient or it is the yield, it may actually be mixed up with the backscattered electron yield, that is the eta E, in the analysis of the experimental data, and therefore, both theoretical and experimental it supports this view. So, for spacecraft charging, so it is often necessary to distinguish, it is not necessary to distinguish between these two terms, and most of the practical purposes it is sufficient to consider this as the sum of these two terms delta E plus eta E as the total probability of the outgoing electrons for the metal surface. So, we will continue the same topic in the next class. We will discuss the there is the photo emission. So, how the photo emission and how we mathematically model, and we will before that we will give you some empirical formula for the calculating the secondary electron yield or the backscattered electron yield. So, this thing we will do in our next session, and let me conclude here today. Thank you very much.